Thank you.
Okay, stuff that's due. We're looking at the rest of the semester, which is winding down quickly. I apologize, I'm behind on grading, homework, and stuff like that. My paper grader and I are working on it, but it's been a little time consuming. I'll get there, promise, before the end of the semester. Okay, let's see. I have this, which is, today's the 27th, so I don't see anything on here that's due on the 27th, so that's cool. No homework due today. Nope, nothing due today that I see. So the next thing that's due is the 6.1 and 6.2 handouts that are due on Thursday. And I think everybody's seen that online, pulled it down, printed it, whatever you needed to do. I gave out some handouts here in Commerce. We're going to talk about one or two of those questions before we get going too far, I think. So that's the next thing that's due. And then so far after that is the construction project, which I haven't finished putting online yet, but it's not till November the 5th. Yes, ma'am.
That's what I was going to ask about. I think the last time I checked, it said a different date.
Yeah, that's what Ryan just told me, was it doesn't say November 5th, so I need to update
But it
that.
will be the 5th.
It will be the 5th, yes. As soon as I get an actual description up and not just the rubric, so it'll be good. But you can follow the rubric to see, okay, these are the things she's looking for. But just wait for it. I'm going to get it updated this week, I promise. Oh my goodness, it'll get there. Okay, so, but the interesting thing is that 11/5 is next week. So Tuesday is election day. Make sure you vote. And then right after that on Thursday is your construction project will be due. So that's next week. And then we just have a couple of weeks left of new material. And then your exam is the week of Thanksgiving on the Tuesday. Okay. So is that the, I might as well write that down. Exam number 2. 24. And for all intents and purposes, this is the last day that you will see me unless we need to have a Zoom meeting or something like that. The review for the final, I will post online. It'll be videos because you guys aren't coming back to see me after Thanksgiving. Remember, they don't want us meeting after everybody gets to hug and kiss everybody that's family and so on. So I will have review days. I will be here during finals week. So if there's somebody, and during review week, so if there's somebody who really wants to talk to me, come into my office hours, that kind of thing, I'm fine with it. But just be aware you don't have to come back to Commerce after the 24th. Okay, so then it's review week, final week. The final is optional. So many of you won't even be messing with that anyway. So that's awesome. Yeah, I think that's it. So presentations, all that we talked about a couple of times. I'm not worried about that. Just the dates are up there. All right, questions? Moving on. All right. I will get that project up, guys. I promise. Just a bit of a craziness on my end of things. We should get better though. Honest. So Ryan has asked about 6.1. There's a question about a slope, he says. Number 4. Okay, AT is tangent to circle P. Find the equation of the line for AT. Okay, so we haven't talked about that. Okay, so we probably do need to talk about that. Do we have a slope anywhere?
We create a slope by origin to that node.
The radius. I'm with you. Okay. All right, so they're utilizing the property that says that if I have a line that is tangent to the circle at the point where the radius meets it, then that line is perpendicular to the original radius. Okay, that's the property that they're going to use. So they're saying this is going to be a 90-degree angle, okay? And they're expecting you to pull out of your memory bank, and I don't know that they should expect you to do this, but they're expecting you to pull out of your memory bank how to write an equation of a line. Write an equation of a line. So I heard y equals mx plus b. Or if you use more of the distance formula, which is called point slope, it would be what?
Y minus y1 equals x times, or n times x minus x1.
Yeah, that guy. Okay, which is basically just the slope formula rearranged, right? They pulled the y's over by themselves. So there's a formula, a couple of formulas out there, and you could, like Brian said, you could go online and find them online if you have to. But this is the stuff that they're expecting us to use. So let me go ahead and put the wait a minute. There. Okay, change in y over change in x, right, is the slope. So rise over run, that's what you would think. Okay, so using the fact that I've got this line coming out and it's perpendicular to this line coming over, we know that this is the origin, 0, 0, right? And we know that this line intersects at the point 3, 9. Okay, so what they want me to do is, first of all, find the slope for this guy. So I'm not going to do it for you, but I'm going to tell you what you should do. Find the slope for the radius, which is from P to A. Okay, find that slope. M here meaning slope, not measurement. Okay, the slope between those 2 points. And then what we're going to do is, we know that, or they're wanting me to pull out this idea that perpendicular slopes, perpendicular lines have negative inverse slopes. Okay, there's a property in the back of your brain somewhere that's probably from an Algebra 2 class that says that, okay? So here's my example. I don't know what this slope is, and I'm not going to use it. So example, if the M for the radius equals, and it's a positive slope, so I'm going to go with 3/4. I don't know, that's not it. I don't know what it is, but if it was 3/4, then the inverse, the negative inverse would be what? Good. You change the sign. It happens to be positive here, so I make it negative. If this was negative, then I make it positive, so negative. And then the inverse just means reciprocal, right, in this case. So it means flip it. So 4/3. Okay. So then once I find the slope for that, so number 2 is find the slope for the new line. And here's how you would do it. I went through the example first, the tangent line. And then number 3 is use the equation of a line. You can use either one of these, either y equals mx plus b or the y minus y1 guy to write your equation. Yes, ma'am.
When you right there for number 2, you said find the
Slope for the tangent line, which is this guy coming down. And the way you do it is by doing the negative inverse or negative reciprocal. In this case, in math, we use the same word inverse to mean more than one thing, unfortunately. So in this case, by inverse, they mean reciprocal. I hate it when they use the same word to mean multiple things. So that's your process for you finding your equation. Yes.
I bet she's gonna say what the slope was for M.
Oh, you know what this slope is here? What is it?
9/3.
9/3, so it'd be 3. Okay, so then
The negative inverse would be
negative,
-1/3.
sure, there you go. Brian's helping out. So yeah, whatever that slope is, find it for their, what is the last word for step 3? Equation, EQN, I'm being lazy, sorry. Equation. Use the equation of a line, one of those formulas, to write the equation. Sorry about that, Jessica. Okay, so that's the process for number 4 on the 6.1 homework. So it's pulling in a little bit of algebra. In this case, it's actually, there is an entire study of geometry that is called Analytic Geometry. And basically they do a lot of algebra in their geometry. So it's an integration of the algebra and the geometry. So they're trying to pull some of those algebra skills that you have from other classes. And they're just kind of assuming that you have those. So if you run into anything like that, where you're like, oh my goodness, it's been 3 years since I took algebra or whatever, just let me know and we can kind of hash it out a little bit. It's expected that you already have that. So, but I know sometimes it's been a while. So, Sarah? Is the rest of 6.1 and 6.2, y'all are doing okay? We covered those properties pretty thoroughly the other day. Nobody's shouting, so. Okay, well, if you run into stuff, let me know. Otherwise, we're moving on. I think we had a take this home and think about it moment the other day. We were wrapping things up, right? We were trying to find all the different properties that the book's giving us. All these different properties that the book's giving us for circles. Sorry, I lost my train of thought. And I think we're gonna wrap up circles today. We're just a tiny bit behind on the schedule. We should have wrapped up on Thursday, but we'll finish them up today, I think, and then we'll move on. It'll be fine, especially with us not using a class period for presentations. We'll be okay. We'll get through all the material. But we were working on some properties, and we were looking at the difference between central angles and inscribed angles. And I think everybody's already agreed that the inscribed angles are congruent, okay? And kind of a little, it's not a proof, so we're not to the point of proofing yet, but a little bit of evidence, let's say, for kids in particular would be that you can use protractors to measure angles, right? Okay. So we haven't used any protractors in this class yet. Not really. In fact, I took that question off of exam 1 because I realized we haven't really talked about it. So one of the things that I could do with young kids is just kind of show them, and we could all do the same similar stuff. And like I've said before, if 20 people get the same answer, kids think it must be true, right? Okay. We know it's not completely true until we prove it beyond a shadow of a doubt. But for kids, that's pretty good proof. So just so that everybody is good with how to measure angles, and I know silly, but sometimes people have problems with this. So if you're like, oh, I can do that, don't worry about it. We're only going to take a second. When I go, and I always am facetious whenever I do this. When I go to measure, I'm going to measure this angle BFC here. And I got to measure it, and I just shove my protractor down like this. Am I okay to measure that angle? No. So Summer's at no. she's weird, right? Okay, so first of all, I know that wherever the vertex is for this angle, I have to line it up with whatever the center of my protractor is, right? So these little orange ones that I sent out in the packages, if you asked for a package, or that you got if you were in class with me, they have a T in the middle. Some protractors have a hole there where you can actually put your pencil and put that on the vertex so that you can line it up exactly. Some just don't hardly have anything. They just have a little line there. So you have to kind of estimate. But I need that to be where the vertex is. And then what's the other problem Summer was shaking her head about? Oh. So if I line up my vertex.
Will be line up to the.
So Maria says the base of the angle, okay, whatever I'm going to use for the bottom needs to line up with what? On my protractor. So here's my bottom of my angle, so to speak. Where do I want to line that up with? Here, the bottom of my protractor?
The zero.
The zero, right? Okay, so I want to line it up with this line. And that's actually, I think, where most people get in a little bit of trouble as they're measuring. If they have it just slightly off, they don't have it angled just so that line lines up with the bottom ray of the angle, then sometimes we get in trouble. So the evidence here for all my inscribed angles being the same is whenever I measure this guy and I come out to B, it looks to me like mine is about 39 degrees. So if all of these inscribed angles are really supposed to be congruent, then all of them should have about 39 degrees. And we've talked about human measurements and human errors. So if it's slightly off, for instance, this angle doesn't come quite to the edge of my circle, right? The vertex isn't quite on the edge. So that might throw my angle measurement off just a tiny bit. In fact, it does. It makes it look like 40 degrees instead of 39, but that's pretty close. And in general, for us, whenever we're measuring things, as long as within a degree or so, I'm not going to stress out about your answer. It's if I think it should be a 40-degree angle. There, and that one is about 39.5, so perfect. They're all within about a degree. When I think it's a 40-degree angle and you think it's a 45-degree angle, that's when we're going to have an argument, right? So that's when we have to worry about how we're measuring our angles. And like I said, a lot of times it's just because we don't have this line at 0 lined up with the bottom line, the bottom ray of my angle. So that's the big thing. Okay. So all of those measure the same. Great. We had already talked about that. We'd already kind of talked about that we could draw triangles or whatever. So I think we're good with that one. The one I sent you home with for you to think about was, what's the relationship between the central and the inscribed angles? So if they have the endpoints of their angles the same, right? Here's the central angle, BAC. Those endpoints. How does this angle compare to the inscribed angle? And you can word it either way you want. I don't care. Let me measure my central angle and see what I think it measures. Because that's what I would do with young kids, right? If they're like, I don't know, I'm just staring at it, not answering you. I would measure it and I would say, look at this. It looks like this angle is about 79 degrees or 80 degrees. How does that compare to the inscribed angle?
It's twice as large.
Twice as big-ish, right? It's about twice the size. Or we could say the inscribed angle is half as large. So either way you want to word that, I don't care. Inscribed angle is half the measure of the central angle with the same endpoints. So that's the important piece, right? They have to start and end at the same spots. If they don't, then we're in trouble. Or you could have said, somebody said the central angle is twice the measure of the inscribed angle with the same endpoints. Okay, either way you want to think about it is fine with me. I think that's somewhere, I think that's in 6.3. And Did we already get, I think we already got the one where we talked about inscribed in a semicircle? Well, maybe we mentioned it, but we didn't get the thing down. We mentioned it at some point. We're gonna do it. Okay, so what about, is everybody okay with this? Central versus inscribed? It's a property for right now. It's a conjecture, okay? Later it'll be proven, okay? Hopefully be proven. And then once it's proven, it'll be a theorem. But for right now, we're just gonna call it a conjecture, or you could even call it a postulate. And as you're working through homework problems, you're gonna use that to help us out. So we'll see a couple of those examples in a minute. Okay. All right, so the inscribed in a semicircle guy. Let's look at one of those. I mean by I don't know what patty paper. Oh, I'm gonna need patty paper to do too. All right, I'm gonna draw a circle. What is a semicircle? Remember when you put your circle in, you need to put the center so you can see it. Semicircle is a half a circle, and it doesn't matter where I put the diameter, right? So I'm gonna kind of do an angly guy just to make him not be half on top, half on bottom, because that's the way we normally draw it, right? I've actually had students before, by the way, that if I always draw, not so much with circles, but with right triangles, A, B, C, if I always draw the right triangle like that, and then on a test, I do like I did with you guys and put them vertical or whatever, so it looks more like this. I've had students tell me that's not a right triangle. Even though it's three-sided, even though it has the little square in the corner that tells us it's right, because it doesn't look like what I always draw it, it confuses them, young kids in particular. So we want to sometimes make sure they don't see the same pattern over and over again. So that's why I said, oh, let's do one that's not exactly the same semicircle we're used to. Okay, so inscribed in a semicircle, what will that look like? Angles, inscribed in a semicircle. Here's my semicircle. Inscribed. What did we say inscribed meant? Okay, the endpoints and so it's inside of the circle, inscribed instead of circumscribed, basically. Circle meaning outside. And the endpoints are points on the circle. What about the vertex? It's also a point on the circle, right? Okay. So a central angle would be the vertex is right here in the center. But for the inscribed, it's one that is, the vertex is on the edge of the circle. So I'm going to draw one of those. I'm going to make him, his endpoints are on the diameter because he's inscribed in the semicircle. There we go. I need some points, so I'm going to call him G, H, and I. I should have probably named my circle, but oh well. If we need it, we'll put it in there. So what do we think about angle GHI? I just wrote angle GHI is inscribed in the semicircle. What's he look like? Ashley's giving me that look. Well, he looks like a triangle. Yep. What kind of triangle? Yeah, I gave you a little hint right there, right? It kind of looks like a right triangle, doesn't it? It looks like this angle is 90 degrees. So again, if I was working with young kids, I could kind of show them a little evidence by measuring it. I can do that here. Indeed, it does look like it is 90 degrees. But the question becomes, well, that one just happens to be right there next. I mean, you made it that way. So let's do another inscribed circle or inscribed angle, shall we? I'm gonna stick this guy on the other side because it doesn't matter which half I draw it on, right? Okay. So if I draw this guy over here and I inscribe him, same semicircle, just the other. What about him?
According to the rule that's above it, for posture, maybe half 180.
Oh, she's got a proof for me. Very nice. Okay, so Ashley's telling me that this angle that goes through the center, I do need a J now. I'll call this guy out here, K. Okay, this angle, GJI, that angle is the straight diameter, but it's still a straight line. It's a straight angle, right? Is 180 degrees, right? And it's central because the J is right there in the middle. And she's saying, look, you're inscribing this guy on a diameter. And this rule up here says that my new inscribed angle is going to be half of the original 180. So it's got to be 90 degrees. And it doesn't matter which side I inscribe on, right? Or how I inscribe. So for instance, I could have another inscribed angle. And this will be exactly what we sent home over the weekend, right? We've got multiple inscribed angles. They all have the same endpoints. So does it matter where I inscribe it at all? No, as long as these endpoints are the same, all of those guys are 90 degrees. So that's yet another follow through for why this guy is going to work for us, because we're cutting it in half. We know that all of my inscribed angles, we could do it backwards basically. We know all the inscribed angles are congruent. So they're all 90 degrees, and then that's half of this 180. We could work backwards if we wanted to. Absolutely. Yay. So what property do we want to put there? Angles inscribed in a semicircle. Here, sorry. No, it doesn't matter where I put them, as long as they're inscribed in a semicircle, they are 90 degrees, right? Or right angles. Absolutely. Kind of cool. Good. You have the proof for it. That's awesome. Yeah, and that's not a terrible proof, right? So that's cool. Okay. If I, so are we all right with this one? I'm gonna move on. If I steal some patty paper real quickly, yeah. And I draw me a circle on the patty paper. I happen to have lots of patty paper. Some of you do, some of you don't. It's okay. You can watch. I sent extra patty paper with different ones. So. All right. What if I cut this circle with parallel lines? Parallel lines. Okay. They're going to be chords. Let me get my handy dandy ruler out, because that makes me a set of parallel lines, right? So that makes life nice. So let me do that. Ashley says Okay, you put some parallel lines through there. The part that's in here, inside of the circle, those parts are chords. Does everybody agree? All right. What do we think about them? Let's call this A, B, C, D. What about those chords? Do the chords have to be congruent? Let's start with that. Y'all are quiet on me today.
No.
In fact, the way I have it drawn, they don't look too congruent, right? So, and I can measure if we wanted to and say, oh, that one's only a little over an inch and this one's almost 2 inches. Okay, so no, the chords don't have to be congruent because that just depends on where I put those parallel lines, right? I could put one way up here at the very, very top, and I could put another one kind of almost halfway. We would see for sure. Those chords don't have to be congruent. So that doesn't help me. Which, by the way, if the chords aren't congruent, what about these outer, they're called the intersected arcs?
Also not congruent.
Don't have to be congruent, right? Okay, so that's one of the properties we had before, that was if the chords are congruent, then the intersected arcs are congruent, but these aren't, so it doesn't have to be. So what other piece of my circle do I have? I just can't hear you.
You have a diameter.
I have the diameter, okay, I don't have it marked anywhere, but I could stick that guy in there. That one goes kind of parallel with the ones I have. We have sectors, but we know that these arcs aren't congruent, so the sectors don't have to be congruent. We don't have this, we don't have this, don't have that, don't have that. I do have this portion of the arc that's in between the parallel lines.
Those are congruent
Why?
because the lines are parallel.
What does the lines being parallel tell me?
The distance between them is the same.
Okay, the distance between them is the same. And if I look at the distance between them and make them congruent, that's actually what? Those are chords, right? The distance between them, A to C and B to D. Okay, and we know they have to be the same because they're between the two parallel lines, right? The only concern might be the angle of those guys, so we can talk about that if we want to. I can show you when these are the same, so we can look at that. If those chords are the same, then what about the arcs that go with them? Yeah, congruent, which is what I heard earlier. Now, if you want to, and it won't take too terribly long, I don't think. You could go ahead and remember what we said last week. Whenever we're looking at any of this stuff, we basically go ahead and make triangles, right? Go ahead and make a triangle. You might find some property in there that helps us from our triangle days. And what we know about those is that they're all radii. So they're congruent. So then if you wanted to prove it, you would what? Look for side, 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 or look for side, angle, side, right? Right, we just don't want side, side, angle, but that would be bad. So we could certainly go that way. With the patty paper, the way I would do it with young kids is I would actually just rip this guy right through the center, kind of like a diameter, like I actually mentioned. Okay, and the two chords that I want to, or the two arcs that I want to compare for this arc AC and this arc BD. So I can just lay those on top of each other. And if I've done it right, we'll see that this chord lines up on both the AC and the BD. And look at those arcs also line up, right? So yeah, we can see they are the same measure. And for young kids, again, if you do it, everybody does it and they all get the same thing, and they're pretty fast. Now for us, we're gonna have to go ahead and prove these as we go along. But there might be a proofing homework in our near future. Be awesome. But yeah, so we can see that. Oh, they are congruent. Awesome. So what's that look like? With two parallel lines. Cut through a circle. Then the arcs between the parallel lines. It's not the intersected arc, which is what we would normally say. This is the arcs between the parallel lines are congruent. So in our example, arc AC is congruent to arc BD. And remember that we talked about that notation the other day, right? Instead of looking like a segment, it's just kind of a little partial circle that goes on top of your, that says arc instead of line segment, the curve on top. Okay, is that all right? So as you're working through and you're doing some homework, if you want to show that, for instance, AC is congruent to BD, these two arcs, then it might be that you need to show that the lines are parallel. Because if you can show those two lines are parallel, then you know these two arcs are congruent, right? So some of that old stuff that we thought we were done with, parallel lines that we started in week 1, is going to come back to haunt us here. Okay, it's not going away. We kind of work with them. All right. And I believe that is the last of the circle. Well, there's one weird that I never use, so I'm not going to make you know it. But if you look in your book, there's a weird one about cyclic quadrilaterals. All a cyclic quadrilateral means is, yeah, I don't care. We never use it. So, but a cyclic quadrilateral means like if I put 4 points on my circle, and basically what they do is they call it cyclic because it's on the circle like this, and we can cycle around. I mean, you could do that with a quadrilateral anyway, so anyway, there's something about these opposite angles are supplementary. So this guy plus this guy would be supplementary, and that guy up there plus that guy down there. And I'm just like, who cares? Okay, so this is not one that comes up a lot, but there is a property still in your book that we're just not going to worry about it. So, but I think other than that one, you're done with all of our properties. I don't care about that one. We never use it. And watch, as soon as I say that, there will be one in the homework. I'll be like, you tell me we're going to have to use this. So it's okay. All right, so that is 6.3. We already did 6.1, 6.2. Now we've done 6.3. And then there's some stuff in your book about proofing, 6.4, 6.5. We'll get to that. Don't worry, we'll come back. We're not going to Not skipping out on those proofs. I know how much y'all want to do them. So we're not skipping them. We're just going to move on, and then we'll pick that up when we get to proofing. 6, 7, well, 6, 5. Let's do that real quick. I don't even think we need to do this one, but it's in the book, and you're going to have to use some of this stuff. But I bet that everybody knows how to do this, so I'm just going to hit it real fast and move on. It's about circumference of a circle. We actually already talked about this one last week when we did our coffee filters, right? So we know 2 things about circumference. One is, well, whenever we looked at pi, we figured out that the pi was the c divided by d, right? So if I want to write that in format of a c, a formula for a c equals, what is that? The actual formula. It's either, there's 2 different formats of it.
2 pi r.
2 pi r, or c equals
ID.
pi d. Absolutely. And I know you guys know this. We've already talked about it. We already did our coffee filters and all that. Your book takes this section. This is why you don't have a homework on this section. I don't think I gave you one of those, did I? Yeah. The one I gave you was 6, 3, and 6, 7. Yeah. Okay. So your book takes this and makes it into an entire homework section where you have to do some problems. So I'm not going to do that to you. We're going to do like one example. And then we'll move on. So let's assume we have a circle and we have a radius. The only thing that's going to kind of maybe catch up with you guys here is naming them properly. So if this guy, the circle is center of G, let's say that this is 3 meters for my radius. I don't care which formula you use. And if you use the first one, you just plug in the radius. If you use the second one, you have to convert that to diameter and then just plug it there. Okay. What do I do? I know. 2 pi times the r, which is 3, right? So C is 6 pi. And just remember what? Your units. Okay. So that's meters. Okay. For our purposes, this is perfect. No worries. There's no need to multiply that times 3.14. I do not care. Actually, 6 pi is considered the more exact answer because we know that it goes all the way out to infinity and never repeats and all that kind of stuff. So 6 pi is considered the appropriate answer. If it says approximate, then you'll multiply by 3.14 and it'll be fine. That was really hard, right? Y'all been doing that since like 3rd grade, right? Okay. So that's why I'm not giving you that homework. If you, however, have never seen one of these formulas, except for when we went over it last week, then make sure that you look through some of the 6.5 homework. Now, we do need to make sure that everybody can do that because whenever we get to arc length and arc measurements, angle measurements, central angle measurements, we're going to use the circumference formula. Okay, so it's expected that you know how to use it going in. Okay, but I'm just, like I said, going to assume that you guys can do it. So that's where I'm headed is for arc length. Anybody need help? Problem, question, concern? We're all good. In your book, that section is called the circumference and diameter ratio, which we know circumference to diameter is pi. Okay. We did an entire activity with that last week, so I'm not stressed with you. I think everybody should be good. And then 6.6 in your book is a section that's called Around the World. And actually, I will say these are kind of really good application problems for things like, what if I spin a bicycle wheel, okay, for 5 minutes at this rate or whatever. So first I would need to find how far did this person go. So you have to find the circumference and then figure out how many circumferences I traveled basically. So they're really good hands-on activity. Again, I'm not going to deal with those too much because if you're in the 361, 362 class, you should see those, okay? The how to figure out how far you're going. So I'm not stressed out about that again. So I'm headed to 6.7. Everybody okay? I know. If you're like, I don't know how to do a bicycle wheel, go look at 6.6 and play with it. Or don't worry, you'll get it whenever you get into that class. So that puts me on 6.7, which is arc length. Okay, and this is where we kind of start, slam on the brakes a little bit. Let's talk about this. Whenever I look at, I've got a circle. Okay, let's call him circle H. I think that's what I'm up to, who knows. Okay, I've got a circle, and I've got some kind of an angle meshed out of it. A central angle. Let's make it about like that. It doesn't matter. We're not going to actually measure them. We're going to use some of our properties that we have. Okay. So let's say we'll do a pretty simple one first. Let's say that this guy is 60 degrees. Okay. And I say it's pretty simple because 60 degrees is going to go nicely into what I need it to go into here. Okay. So what I want to know is people are like, what's the difference between the angle measure, the central angle measure here, and the central arc that's created? Okay, the intersected arc here. The arc length, we talked about this a tiny bit the other day. This is length. Okay, which is distance, which means I can put my string on it and measure the distance from this point to this point, and it'll be like inches or centimeters or something like that. Okay, that's a length. That's different than the angle measure. Even though they're on the same angle. Okay, so the angle measure here is 60 degrees. Okay. The arc measure or arc length is what we're wanting to find. Okay. I need one more little piece of information, and it can either be the radius or the diameter. It doesn't matter, because if they give me the diameter, then I'm going to figure out what the radius is. So let's say that this particular one is 2 centimeters long. That little H2, I don't know, let's call it I. Hi. Sorry. That little radius. Two centimeters. And if we have that, then we have plenty to figure out what we need to figure out for the arc length. Believe it or not. All right, here's what we're going to do. First, we're going to figure out what portion of the circle is that angle. 60 degrees in this case. Portion of the circle is it? Now, how in the world will I figure that out?
Divide the angle measure by 360.
If I went all the way around angle measurement wise in the circle, the whole entire circle will be 360 degrees. Everybody agree? Okay, so I'm hearing that what I need to do is 60 degrees divided by 360 degrees. That will give me a fraction, right? Sometimes they're ugly fractions, okay? If I had given, that's why I told you I'm going to choose wisely what I'm doing. If I had given you like 50 degrees here, then it would not reduce as nice and pretty as what we're doing here. And sometimes they don't, okay? But for this one, I want to know what portion of the circle I'm looking at whenever I look at this central angle. So what is it? Okay. 1/6 of the circle. Everybody agree? Okay. So this sector right here that I've shaded, guess what? The arc length that's here, what portion of the circumference do you think it is? 1/6, exactly. So I need to use the angle measure to figure out the portion that I'm after, and then I'm going to use that on this arc length here, okay? Which means that our arc length that we're after is 1/6 of the circumference, exactly. Okay? All right, so then I need what? I need the circumference, right? So, but that's why we had 6.5, and that's why I at least touched it, but I feel like you guys will be okay with it. So what about that? My circumference. Okay, so I know that it's 2 pi times the r, which we said was 2 centimeters, and Ryan says that that's 4 pi. Don't forget, I need to multiply that by 6, but the circumference is 4 pi. Everybody agree? Okay, so now I need to multiply that by 6. Again, this isn't beautiful, but it's not horrible. 4 pi over 6 will reduce to 2 pi over 3. That's not terrible. We leave it alone. Okay. Now, what about that number? Let's just kind of think about it for a second. It's like 2 times, let's just say 3. 2 times 3, it's about 6, a little bit bigger. Divide by 3. So this thing is a little bit bigger than 2 what? Centimeters. Good. I'm out of space. I'm going to put it right here. Okay. So the arc length that's represented right here is 2 pi over 3 centimeters long. Okay. So it's going to be a little bit of, oh, I got to refer back to this other skill, and then I got to refer back to this other skill. Like we had to refer back to, oh, the circle is 360 degrees. We knew that. We just haven't used it in a while, right? And we know how to use a circumference. And so then it's just what portion of that circumference am I after? So that's what basically boils down to. And that's how they connect the arc length to the angle measure. Okay. In a testing situation, what I would probably do is make a bit of a table, okay? And I'd ask you to fill stuff in, like what is the radius? What is the circumference? Like use those skills. What portion am I looking at? So it would be like, okay, you have to know it's 60 degrees, divide by 360, that's 1/6. Okay, so probably a table that I can kind of get you step by step to go through the process and then tell me what the arc length is. That's what I generally tend to do on the test. All right. So that's where your homework is. So let me throw that at you. I have not loaded this into D2L yet, but I will. Just as soon as I get back to my office, I will try to do that and try to get your construction project. Okay, so I'm staying away from book pages as much as I can lately because we have that book discrepancy, right? So here we go. This is another kind of handout. There's not a lot of work space here, so work it on your own paper and then upload both. Or you can just copy this over onto your own paper and you don't have to upload this. I don't care. So this one, 6.3, is about arcs and angles. And so you're going to use all those properties that we looked at last time and this time to get that covered. I feel like most of it's pretty good. You can see like a kite coming in here. You know those properties about kites. So if you need to reconstruct something that we did last week, then feel free to do that. I've told you guys this before, questions like number 9 down here, right? Where it says find the lettered angle. To me, those are a bit of a puzzle thing for you to work through. I love those, so make sure that you can work those. And don't go, oh my goodness, that's like 12 things I have to find, right? Do them one at a time. Look for stuff you know, and then move on. Okay, mark the picture. If you need to make the picture bigger on your own paper so that you can mark all the angles, then do that. You can do it. Okay, but I really like those. And look, here's the circle, and look, those are parallel lines going through it. We talked about that today, right?
I have a question about the construction project.
Mhm.
Are we going to be using GeoMeter?
GeoGebra.
Oh, GeoGebra.
Yeah.
I already had GeoMeter, so
Oh, yeah. Okay, no problem. Yeah. It's just not going to be Geometry Sketchpad, that's what the problem is with the thing. My original project says Geometry Sketchpad all over it. So I'm having to redo it. It's just taking me some time to make it GeoGebra instead, but yes. Absolutely. Okay, so when I look at this guy, for instance, because these are parallel lines, what do we know about D here from my parallel line properties with this 50-degree guy down here? It better be 50 degrees because they're alternate interior angles, right? Yes, ma'am, absolutely. So what all of those things that we've been dealing with for the last 10 weeks, you can't drop them, right? They come back to see us here. So D, we know 50 degrees. Boom. There's your one answer for 9. Number 9 has 12 answers, so there you go. But yeah, bring all those things back to you. It'll be great. So that's the first piece. And then the second piece is the 6.7 homework. And this one, I just touched on a little bit. So my plan is to let you play with this a little bit and take it home and work on it. And then on Thursday, I would like to look at problems that you have with this one, okay? Because 6.7, it's a little more mathy, it's a little more algebra kind of skills. So take a look at this 6.7 and bring in questions on Thursday that you want to talk about, okay? And then we'll do that. And then I'll feel like, okay, 6.7 we covered. And then that's going to be it for circles. We're going to move on in our content. Yay. Yay. All right. Let me call roll. We're a little bit early. Oh, man. I know y'all want your money's worth, and that 3.5 minutes, dude. If you must have your money's worth, you can stick around. It'll be okay. All right.
So there's nothing due today. Next one due is 6162 on Thursday.
Correct. 6162 on Thursday. Mary's question, yes, 6.3 and 6.7 will both be due on Tuesday. Start work on those, but ask me questions about 6.7 on this week on Thursday. I don't know where that is. Put it here. What is that? That's
Third.
the third election day. There you go. Okay. Yes, ma'am. All right, Samantha, I see you. Maria's here. Christina. Saw you earlier. There you are. Mary, I see you. Brian, I got you. Ashley, I got you. Summer, I got you. Alexis, got you. And Amandre, I got you. If you're out of here, have a great day. I'll see y'all on Thursday. Aaron, I got you. Jessica, got you. Matt, I got you. Elijah, I got you.
323.
Okay, so I don't see Gabriel, Caroline, Amberly. No Amberly today. Or Cameron. Okay, I think we're gonna have a participation quiz. I'll get that out too. Have a great one.
Thursday I was